All right, Sam, I think you can start the show.
Sure. I do remember seeing this on social media. If you haven't used Zoom recently, the when you're being recorded, instead of a box popping up in the middle, it's at the very top of your screen. There'll be a little small dialog box you can click OK or something like that. Okay. Yeah, so welcome everybody to the first 2024 edition of VAST. This is the Virtual Astronomy Software Talks seminar, where we will have two great speakers talk about their software for about 20 minutes, followed by 20 minutes of open discussion. And if you would like to submit a talk, then you can go to the VAST, the GitHub page and the VAST GitHub page and file a GitHub issue. You can follow the format that other speakers have used in the past. And like Michael put in the chat, if you have questions for the speakers, put them in the chat and we will get to those. We'll answer one or two questions after each talk. And then at the end in the open discussion, we'll try to get to, we'll get to as many questions as we can. And yeah, Alice put the link to the web page in the chat, so feel free to visit that and check it out. And so yeah, like I mentioned, we have two great speakers. Brett Morris is going to talk about Jdaviz, and then Kaze, where did you go? And then Kaze Wong is going to talk about Show Your Work. And so yeah, we'll start out with Brett, and he'll have 20 minutes to talk about his project, and then a couple minutes for questions. And so yeah, I think I will pass it off to Brett.
All right. Hi, everyone. Thanks for turning up today on what I assume for you is also a very, very cold day. And I hope to warm you up with the thrilling excitement of data visualization and analysis tools such as JDA-Viz. If you don't know what this is, I'm excited to show it to you. And I've sent to the chat a link to the presentation that I'm about to be sharing from so that you can follow along on your own time or look at this later also if you choose. There are many links throughout this presentation that you can follow. If you open the link to the presentation, you can click on any underlined word, which will be a link. And the format of the presentation that I'm about to give to you is that I've got a few slides as introduction to what this software toolkit is. And then I'm going to show you an example interactively in real time at the end. And if we like, during questions and discussion time, we can go into more details about any of the topics that I may cover. So I'll introduce myself. My name is Brett Morris. I am a software engineer who also does research at the Space Telescope Science Institute. I currently support JWST through the data analysis tools, which is the team that makes JDA-Viz, as well as the Roman Space Telescope, which I work on the pipeline for. And one of the things that we have to do at Space Telescope that you likely also have to do at some point in your life as an astronomer is to interact with your data. And there are many ways that you could do that. I'm going to try to show you one way that you could do it that you might not have heard of, or you might not have seen all of the tools within it, and try to convince you that it might be helpful for you in your work. First, I'm going to tell you a short story. 4 years ago, there was this spacecraft that was sitting in California, not quite lazing in the sun. I'm glad it wasn't in the sun. It was in a relatively dark room, getting tested, getting spruced up just before Christmas. And then 3 years ago, I was doing a postdoc in Switzerland, and while I was there on Christmas morning, I was watching NASA TV in a friend's living room, crying as my friend Nicole was on NASA TV, talking about the launch of a space telescope that the future of many of our careers was riding on. And this was 52 minutes before launch, and I was really, really feeling it. So I was happy to see Nicole's face on the screen. Then, of course, everything went okay 52 minutes later. And so 1 year ago, we got some really beautiful images from the James Webb Space Telescope. And when it goes through the magic black box at the Space Telescope Science Institute called the Office of Public Outreach, they take the data that comes from the telescope and turns it into these unbearably, incredibly beautiful images. And I often think about how much subtlety there is in producing an image that looks this nice from data that we know contain all kinds of artifacts and subtleties that need to be reconciled in order to make a color composite like this. And some of the tools that we have for doing that are quite difficult. And what I'm about to show you is not a visualization tool that makes visualizations that go into press releases, but ones that could be useful in your research. And I'm going to show you how you could explore your data. Although before I do, I'm going to say my update from this last year is that we've now reached the point where these press releases are available as Christmas ornaments. And so this Christmas, I actually got recommended in an ad for one of the press release images to go on my Christmas tree, and I thought that was amazing. But more relevant to your life, let's say you got an email from Space Telescope that says your JWST data have arrived, or your PhD advisor says, actually, I really need you to open this FITS file, or even worse, this ASDIF file that somebody created for me that I need you to open. What I'm going to show you today is a tool called Jdaviz that allows you to open those data on your laptop today so that you can start investigating what the data contain within them and what science you can do on those data. These are the data underlying that Cosmic Cliffs press release, which I've loaded into Jdaviz to show you that I can combine them also with images from HST. These are ACS images of the same part of the sky underneath, and I'm putting them together in a kind of silly but also kind of beautiful color composite, just to show you kind of what we can do here. So what is Jdaviz? What does this thing do? Jdaviz is a package that allows you to visualize and interact and analyze your data. There are different ways that you might want to view your data, depending on what kind of data you work with. And there are corresponding parts of Jdaviz for each of the kinds of data that you may interact with, because you wouldn't look at a spectrum the same way you look at an image. And so in Jdaviz, there are different kinds of tools for different kinds of data. There's ImViz for images. There's SpecViz for 1D spectra. If you work with IFUs, if you work with MIRI, we have CubeViz for working with spectral cubes. And there's also MOSViz for multi-object spectrograph outputs, which will contain both the image of the field that the spectrograph is going to be taking spectra from, 2D spectra, as well as the reduced 1D spectrum from the 2D spectrum, and a table of all of the objects in the spectrograph's field of view. So we've got all different kinds of ways to look at your data depending on what your data are. Here's a quick rundown of what they are and what they look like. This is what the view looks like when you open up ImViz and you import some data into it. These are observations from JWST, I believe. And here we are looking at the viewer, which contains our data, as well as this toolbar at the top, which is common. It contains many common features to all of the different ways that you might look in data across Jdaviz. So you can import new data, you can add separate panels where you can load different combinations of data, and then lots of other tools. And I'll give you an idea by interacting with the tool during this talk to show you what that looks like. We can load multiple data sets. We can load them into different colors and different layers, and then change the opacity to make color composites. That was one of the things that I showed you could do earlier. Here, these two images are aligned by their WCS, so that they're aligned on the sky, not by their pixels, so that you can make composites of images that were taken in any orientation or with any dither pattern. This works for arbitrarily complicated data sets. So here we've got data from many different telescopes, which is kind of a version of the slide I showed you earlier. In orange and red, we've got some NIRCam imaging of those cosmic cliffs. We've got ACS images in the background. And then these big yellow squares are TESS pixels. TESS, of course, is nearly an all-sky survey, and you can see that in a TESS full-frame image, a pixel is huge, right? A NIRCam pixel contains about 600, one TESS pixel contains something like 600 NIRCam pixels. So you can really see how big the difference is on the sky, and that really a TESS pixel of this one bright star spreads out into a PSF of several pixels that span many, many actual objects that are contained within those pixels. You can see why dilution and contamination are challenging in TESS observations, right? So this is the kind of thing where actually seeing it with your eyes would really help you intuit what's going on within that test pixel. And so visualizing your data would be super helpful. Let's say you have 1D spectra. Here, I've loaded a spectrum that has 2 emission features, and I've highlighted 2 regions where I've selected each emission feature in its own subset. One of the cool things that we can do in Jdaviz is that we can fit models to these subsets, and these models come from a predefined set, including features like Gaussian, Lorentzian profiles that can also contain linear or polynomial trends in the continuum so that you can fit for parameters that matter to you, as well as using tools built into spec utils that give you line analysis tools at the ready. So just from selecting the subset that has this emission line, you can then look in the line analysis plugin, which will tell you what the flux was within that line with units and uncertainties, the equivalent width, the full width at half max, and the centroid, for example. So you get all of that for free in an interactive workflow. Here's what CubeViz looks like. When you have a spectral cube, you can look at one image, so a spatial image at one wavelength at a time. The wavelength being represented is denoted by this orange line here. And the spectrum that you're seeing down here, this 1D spectrum, is a collapsed spectrum of the entire spectral cube. I believe this one is just the sum of the flux within each image at each wavelength. And when you use CubeViz, you could slide around and select different wavelengths to see what the image looks like at each wavelength and compare on an emission line to off an emission line. And then also, since the instance of the spectrum down here is a spectrum viewer, we can use a similar process as before to do line analysis, and we'll get there in a moment. But in order for that line analysis to be really useful, we might want to select regions within the IFU to see what's going on, because I showed you that there was a feature that popped out on an emission line and it disappeared when I went back towards the continuum. So here I've drawn a subset on the central source, and then I drew a second subset on the one that popped up. And now it's giving me real-time collapsed spectra of those 2 subsets. And now if I zoom in on this region where those emission lines are, I could, for example, fit Gaussian profiles to each of those emission features, see that the means are slightly different because one is redshifted, and start to do science with that, right? So we can do the interactive workflow that gets us to a first order rough science answer that might be really useful to you. The Viz tool that I will describe the least is called MOSViz, and here's what that looks like. And I'm describing it the least because it's sort of the most complex. This viewer has the image of an object in your multi-object spectrograph with the footprint of the slit over the object. Over here, we have the 2D spectrum from the spectrograph, which gives you the spatial dimension and the dispersion direction here. This is the extracted 1D spectrum that came from the 2D spectrum above. And if you were to click on each row, it would take you to a different object in the spectrum. Now, if any of this looks interesting or useful to you, there are several ways that you can use the tool. It's a Python-based tool, and you can pip install it. You can use it from the command line, which allows you to just run Jdaviz and a file name, and it will open your web browser. Within that web browser, there will be the instance of Jdaviz that looks like this on your tab. The other approach would be to use it from a Jupyter notebook, and I'm going to demonstrate that in just a moment. You would import the tool that you want to use and load your data into it from a Jupyter notebook. And then interactively, you can use the tool within the output of a cell in your Jupyter notebook and get inputs and outputs into and out of that view from your notebook in real time. So if you do clicks and fits and operations on your data in the viewer, you can always export those data within the notebook at the same time. So you can go into the notebook and into the viewer, the interactive part, or out of the interactive part, and use the API from Python to do the same commands. And lastly, there's a way to use all of this through MAST. MAST is where all of the data from Space Telescope are stored. And if you're on the Space Telescope portal, you can look up observations. Here I'm looking up a particular JWST observation of Jupiter's moon Io, taken with MIRI as a spectral cube. If you find data sets that have this icon, that will open CubeViz for you in the browser. And so if you click that, it's going to show you a page that looks like this. This is CubeViz, which is the viewer for spectral cubes I showed you just a moment ago. And this is Jupiter's moon Io. It is spatially resolved here, and that hotspot is a volcano. And you can move on and off of absorption features to see if the volcano is hotter or cooler at those wavelengths. You can start to do science with your eyes and your brain, and then fit blackbody models to the spectrum and do actual science too. One of the neat things, though, is if this is a data set that you want or like, you can click Open Data in the upright, and one of the options it will give you is to give you the Jupyter notebook that opens this data set locally and downloads it for you. So you can use it in the browser, and you can also use it locally. Now, I believe I have like 3 or 4 minutes left, and if that's right, I'm going to use that to show you some quick things, some actual demo, and also just where the code lives. So Jdaviz is under the Space Telescope GitHub, and it's very actively developed. There are currently 6 full-time developers allocated to Jdaviz. We are working on it all the time, and I am one of them. We have really extensive documentation. So if one of these tools is most useful to you, you can click on the one that you think you're going to use, and you can figure out how it gets used and also how to use it through the user interface and the API so that you can do all of the things that there are to do in the tool. And like I said in the presentation, here's what it looks like on MAST right now. So in order to use this web page, you don't have to have Python installed on your computer. This is fully in the browser. And so we can click inside and outside of spectral features and see how the image of Io changes as we look in the continuum where the surface thermal emission is coming from at 7.6 microns, or in an SO2 absorption band at 5.4 microns, and see the volcano. I think that's really fun. Here's what CubeViz looks like in a notebook, and this is the end of my talk. It's just to show you that the notebook workflow is actually really convenient. There are demonstration notebooks available in the Git repository, and the notebook that I'm showing you is one of those notebooks. So you can use this notebook on your machine too. This is what the output looks like in a Jupyter notebook. It works just like I advertised in the talk. We can click around and see different slices through the spectral cube and look on an absorption feature or an emission feature and see how the slice changes and look at how the galaxy is doing interesting things. We can select subsets to produce in real time live collapsed spectra from that region that I just drew. And we can select spectral subsets within there. So I'm going to zoom in on that subset that I just created on the spectrum. And we can do lots of operations. Like, for example, we can do simple analysis on the line. So let's take for the subset that I just drew and the spectral subset that I just drew. Let's do line analysis. So the equivalent width of this line is this, and the centroid is this. So for example, you could do all of these things really quickly and really easily. If that was insufficient, you could use model fitting to fit a model of your choice, like a Lorentzian or a Vogt profile, to that same line and get out the physics that you care about. And the very last thing I'm going to show is that all of this works in both directions. So we can also say, I just drew an interactive region in the output. Please show me what that region was. And here you can see that this subset that I drew has these coordinates in pixel space. And if I adjust the subset, or if I create a new subset, it will give me a different output each time. And so here I moved an existing subset, and the output will change its value for subset 3 because I moved subset 3. And so everything you do in the output is interactive and works at the same time as your notebook. So you can continue to use science workflows that require you to use your notebook at the same time as you use your interactive viewer, which means you can load new data in or export results out and do your science in both directions. So that's where I'm going to stop myself. Happy to take a few of your questions, and I'll be sticking around for the discussion, of course.
Awesome. Thank you, Brett. That was a great talk. I want to first apologize for not introducing you. I'm new to MC.
No worries.
I will I will improve on that in the future. And so yeah, I'll hand it over to Michael to take a couple questions before we move on to the next presentation.
Sorry, my mute button is uncooperative. Indeed, that was a very nice talk. I have a quick question, and you said this is Python. What toolkit are you using for the interface?
So the stack is deep, is the short answer. There's a lot of things that we depend on. Most of the interactive visualization backend is Glue, which allows us to link multiple data sets together across multiple viewers.
But for the GUI itself?
The GUI itself is built on Glue and Glue Jupyter, and also lots of other tools.
Great. It looks very nice.
Thank you. Thank you.
My internet connection is a little bit slow, so let me scroll here. All right, for IFU cubes, does the user have access to each bundle?
I'm not sure what a bundle is.
I'm not sure either. It's in quotes.
Oh, the location where the spectrum was taken before any convolution or gridding.
Depends on the spectrograph, I think is the answer. That has to do with the way a pipeline would work more than it does with the way the Viz tool works. Does that answer your question?
Probably. I'm thinking about SD FITS files, which is like an IFU, and they have a spectrum at each point and random point on the sky, more or less. And then you don't get a real regular cube like you showed until you do the convolution.
Right. So what we're doing here, we're a Space Telescope Science Institute project, and so we're supporting JWST instruments and observing modes first, and the JWST pipeline will give us products that are already gridded. And so it does work, for example, on Mongo cubes, which are hexagonal and a bit different. But to roughly answer your question, I think the answer is no. We assume that by the point it reaches us, it's already reduced to the point that that's not something we would be worried about.
All right, we'll have time more after Kaze's talk, so I'll turn things back over to Sam for the introduction.
Yeah. So yeah, so the next talk is going to be by Kaze Wong. So again, I don't have introductions prepared. So Kaze, if you wouldn't mind maybe giving yourself a brief introduction, I'll just say that he is going to talk about Show Your Work, which is has to do with software licensing. And so yes, take it away.
Hello, everyone. I'm Kaze Wong. I'm a postdoc research fellow at the Flatiron Institute in New York. I work on a multitude of things, from gravitational wave, data-driven astronomy, machine learning, and stuff. But recently, I have been putting a lot more effort into like open source software development and reproducibility in scientific publication. So today I'm going to talk about Show Your Work, a package. I'm actually not a maintainer or even like a developer for the package. I'm just a user, which is a package. Show Your Work is a package that is developed in Flatiron by a former postdoc, Rodrigo Luger, and Dan Former-Mackey, who is a research scientist here. Dan was supposed to give the talk originally, but Dan recently have a kid, so that goes off the window. So I'm basically a substitute of Dan. And today this talk is not so much about all the demo that I'm going to show you, but about some opinion on how we think that we should approach reproducibility in scientific publication, and show your work is a package attempting to do that. And yeah, I'll just get into the meats then. So before I go into what we want to achieve with show your work, let's talk about why reproducibility is important first, like for a split second, in case you're not very aware. So a couple of years ago, there was announcement on something called, like, from the Bicep group that talk about they have found a gravitational wave in a primordial gravitational wave in a CMB, which is, ultimately it led to a lot of cross-check because it was a big claim, because that was before the LIGO detection of gravitational wave, and people cannot reproduce the analysis. And when people can, it found that the source of that is actually not so much exclusively primordial gravitational wave, but it could be dust and stuff like that. So that's one hiccup in the history, that reproducibility, it's important to show that if your work cannot be reproduced by others, then that may add some shade on the study. And more recently, there was this LK99 superconductor that was raving over the internet, that people are saying, well, we found room temperature superconductor, and that drives a lot of drama and on different quantum journal and Twitter, of course. And very quickly, people found that, oh, this is actually not exactly a room temperature superconductor. There was a lot of uncertainty going behind. And I'm more working on the machine learning side. And one thing that happened very, very common in the machine learning world was what you're showing here. So you'll get paper B that talk smack about previous papers, like, their work is not great, but our work is awesome. And then later on, paper C will come out saying that, well, actually, paper B didn't do great, and paper A is even worse, but our thing is great. And if you try to reproduce anything in machine learning world these days, which is as much as they try, it's quite hard, because that depends on what kind of cluster you get, what kind of data you get, even the seed, like the random seed that goes into initializing the weights of a neural network and stuff like that. And people usually don't give all the detail that needed to reproduce their research. And that's kind of sad, because then you can make all this big claim about, oh, we found this thing to be very useful, but no one else can do it. Then it's not quite desirable in terms of science, right? Because others really need to get into the result before they can say, oh, we agree with you. So that's the background that hopefully I've show you. Reproducibility is really important. And okay, so now what is show your work and what show your work is trying to do? Let's say someone wrote a paper and you read it. It's great paper, awesome content. But these days computation and all the steps could be quite difficult and convoluted. And the idea of show your work is, when we write the paper, hopefully there is a workflow management tool that will collect all the ingredient that goes into finally compiling a paper, all the way from your script, your data, the generate the figure, and the equation derivation, all of them into your paper. So show your work, it's kind of like a bundler or a workflow management tool that helps you bundle all of them and put them together with a paper. And I won't go into too much detail of how to use it, because it has a great documentation page, and there are numerous examples on the web that show how you can show your work. But just to show how easy is it to use, basically you do pip install show your work. All right. You need to clone the article repository, and then you build, and there will be a PDF. And later on, we'll have a look of how the repository will look like, what actually the bundles look like in a second. And then it will generate a PDF. All right. We will come back to this, don't worry. And what does the product look like? Let's look at the final product. What is a show your work paper? So this is one of my paper that get published in AppJ recently. I didn't updated the link, but this is a paper that I prepared using show your work, and you can see this is actually an older version of show your work. You can see some of the stem here, and in the abstract you can already see some anomaly here. There's a GitHub icon here. We're gonna come back and click on it, but basically this will bring you to a repository which has my source code, which is not new, but all the other script and data or links to the data that generate the content in this paper. So if I scroll down, into I believe it's figure 1. So this is one of the figure that like we have some complex. Actually, maybe it's better to never mind. So this is one of the paper that one of the figure that we generate. It's posterior samples for a particular system that we analyze in our paper. Now, normally people will look at the figure and say, this makes sense, this doesn't make sense. But ultimately, how do I convince you that I didn't just cook up some random number generator and make this posterior, right? So that's important. And to validate that, so there is like 2 icons in this figure that you can click on. Let's see if that works. It should open. Hold up. Oh, the exit. Does it come up? Click. Oh, sorry. 1 second. Oh, there you go. Oh, that works. So once I click on the icon, it'll bring me to Zenodo, which is, well, it doesn't necessarily have to be Zenodo, but that's the choice at the time. That store all the data that goes into generating that figure. And not only the data, but also the script that generated it, and on GitHub. It's going there. So I click on the icon, and basically it is linked to the repository that I compile and show your work prepare for this particular paper. And you can find it under script. This is saying figure 1 corner plot, and all the configuration and steps that we go through to make those make that figure. All right, so we're trying to be as open as possible. Like, what is that line? This is the median. Where's the data? Which cosmology we use here? So on and so on. All right. So the hope of show your work is really to expose the underlying workflow behind the paper, every figure, every result, as much as possible. And you can see every figure has the data linked to it and like the script links to it. All right. And in a more recent update, like the styles change a little bit. This is another paper that I published with like show your work recently. I think it's published also in AppJ. And the style changed a little bit, but the spirit stayed the same. Every figure that we generate, you can actually generalize this to table or equation even, but we didn't take it that far. But yeah, everything that is prepared under show your work, you will have a script that even goes into how the quantile is generated and compute. So people, in principle, you clone the repo and you just do show your work build, you'll get exactly what we have in the paper. At least that's the dream. Okay, so that's the idea of show your work. Now, let's have a deeper look of the repository and how the repository layout look like. So this is the the first paper that I've shown in the previous slides, and like this is just the README. But basically, in the source files, there will be a couple of things. There will be the tag file. This is the main tag, which is the LaTeX file that goes into compiling the paper. And show your work, it's a package that you can import in LaTeX. I will zoom in a little bit in case people can't see it very well. So show your work is a package that you can import in LaTeX, and basically a bunch of macro. And if you go to a figure, let's see, where's the figure? Can I click on this guy? Oh, here. There you go. So this is, I believe, is probably the first figure. And now on top of the usual stuff like your figure, include graphic, caption, and label, there's an extra line that is called script, which is macro defined in show your work that basically link this figure to the script that is also in the same repository, which is like script here. So that was the script that we've seen earlier in the talk that goes to that. So show your work, it's basically bundling all this information up and put them all out there so people can access it and reproduce, follow the step very easily to reproduce whatever goes into the paper. So that's the idea. There's actually a little bit more than just, this, because show your work actually have a lot of infrastructure working with GitHub Action that will build a paper for you on GitHub. So it makes sure that not only you can build it locally, because sometimes you can have dependency issue, but hopefully there's like external environment that can build your target as well. So you see there's like article PDF icon here, and if I click on it, oh, it download the PDF sometimes, like so just download the PDF and there you go. This is the PDF. It actually compiled it on GitHub Action. So if it fail, if the build is not it is fail here, that means maybe there is some hiccup in like dependency and so on. So you know that this can be tested a little bit better. All right, so at least that's the dream, at least that's the past. Now I won't actually go into how does it work. It's actually pretty fascinating. Underlying, you use something called snake to do all the rules and figure out the fancy math and some graph math behind it. It's an amazing page that I encourage people to read it because I think I'm slightly short in time. And go read this. Basically, track all this dependency, show your work, track all this dependency, and know which figure depends on which data, and fetch them and compile them. But I really want to get into some problem that I have with show your work. If you're very hyped about show your work, it's like, this is great, I'm gonna make all my article reproducible. It's awesome. I very glad that you feel that way. But also, it's not without problem, and we're trying to solve those problems right now. Again, actually show your work. It's a working thing, and you can install it today. You can use it now. As much as we want it to be completely reproducible and like to achieve an ideal, it's not quite there yet. And again, I'm a user, so I'm well aware of these problems, and I think it will be fair. It won't be fair if I don't say them, but it will be even better if we're aware of the problem and we can fix them, so we get a better version of show your work. So I'm going to talk smack about it, basically. First off, so yesterday I talked to Dan about, okay, how do we improve show your work, and we were talking about something. This morning I get an email from my student who used show your work to prepare a paper, and it's like, which is a paper that we published about a year ago, and now it's going through on archive, and now it's going through referee. We like finally reaching the final stage, and my student told me, well, it didn't compile. I don't know what happened. I updated show your work, and my thing didn't compile. And I figured that it's like a dependency issue. It's not show your work itself has problem, but show your work have like a pretty large dependency tree, and those get updated, and it has some breaking dependency, and that causes some problem instability, because you want your paper to be written once, and once you freeze it, locked it, and it will be compilable. Like it can be compiled in the future, right? But obviously, this is not at least always the case right now. So that is a problem. Maybe 2 years, 3 years later, your the compilation of the draft may have some problem. So that's not ideal. Second is like it depends on Conda. I'm a personal I'm not a fan of Conda because how they manage the binary, and I personally am like a minimal dependency person. So getting rid of some of the dependency will actually help with problem one as well, which is some of my personal thought. And finally, non-ideal reproducibility. So when I say we reproduce the paper, that there is a catch. Like Stuart observer will notice that, wait a minute, you have some data stored on Zenodo. Like, how is that data generated? And indeed, sometimes our workflow, for example, you do an n-body simulation that is large scale, it run on a cluster or something. An end user may not have the best way, like resource to regenerate those simulations. So they rely on the data that you generate. In some of the workflow that show your work is originally designed for, it works because it's smaller task. But like for bigger tasks, it's not quite exactly reproducible in the sense that they don't really run every code that you do. Maybe you get to this plotting stage, as we did, because we have a lot of data there. So how do we go about that? How do we solve that problem? It's an open issue. All right. So future of show your work. So I think I have like 1 or 2 minutes maybe. I want to talk about like how show your work might evolve in the future. It's still a little uncertain, but I truly believe, with this open source community, the more we think about this and work on it together, and everyone will have a better product, and everyone will benefit from that. So one thing, it's to solve the dependency problem, we want to introduce some of the technology that people have used in many other scenarios, like log file. There's Pixie in Python, or we can use Rust that also produce a log file. Basically, when you compile the code, it will generate all the dependency at the time. So in the future, if you want to rebuild, you'll always take the same set of dependency and compile that instead of running with the most updated version of everything, which may not be backward compatible. The second thing is, so we mentioned about SnakeMake is the backbone of Show Your Work, but SnakeMake is actually a fully fleshed out code that they have and do way more things than what Show Your Work needed. For example, it know how to schedule tasks on a cluster. It know how to talk to Slurm or whatever high performance computing environment manager that you use. And we don't quite need that. The main thing that we need is how to figure out the dependency, which is like to figure out the DAG, the direct acyclic graph of your target, right? Like given a paper, what is the dependency tree? We want that. And basically that's the main thing that we want. Maybe we want to abstractize that so we don't depend on all the other thing that SnakeMake has, and we won't break on that. But that's one thing that we're considering. And one thing that it's near and dear to me is I write a lot of code and I see people use a lot of my code, but ultimately, you know, even you have good documentation, you can anticipate how people use it. No one really uses it exactly the way that you intended to. So if we build some spirit of Show Your Work in the sense that, okay, maybe at the end I produce a figure, I produce some code or some data, and there's always a traceback and a dependency tree of how each step goes into that. In even analysis, that would be great. Basically, we're not only using Show Your Work for paper, but also every computation step. And that'll be great, right? Because now your student can follow exactly the step how you do the computation. And that'll be stellar. So this is some of the direction that we've been thinking. There's not a lot of active development right now, but there should be soon in the coming months. And to end on like a more positive note, I really like Show Your Work in the sense that it has all this infrastructure built into it that allows you to use GitHub Action. So instead of like if you're working with a student, like more senior people will understand what I'm talking about. So if you're working with a student and you look at the paper, you see, wait, this figure is not quite right. And usually what you need to do is like, okay, tell the student, go back, change your script. Can you make it a little bit better? And they go back, you know, open their code, work on it, and come back with a figure. And it's like, this is not what I want, now change it, and you waste another week. But with Show Your Work, because everything it's on the GitHub repo, you can just pop it up, right? All right, like the figure doesn't look nice. This is the script. Now go in and change this line. Awesome, sorted. And you change it on the web, pushed it, the figure get compiled again. You can just open it on GitHub. Awesome, you know, done. And I think that part of Show Your Work is my favorite, that it helps you to smooth out the workflow in paper writing quite a lot. And if you have not tried, I highly encourage you to give it a shot. And if you run into any problem, me, Dan, you know, other developer are quite keen on answering them. So yeah, like that's about it. And yeah, take question.
Awesome. Thank you, Kaze. That was a great talk. And very knowledgeable considering that you're not a developer. You just use the code. You know a lot about it, which is great. Okay, so I guess we'll take a couple questions first, specifically on Show Your Work, and then we'll turn it over to the open discussion. So I'll pass it over to Mike to handle some questions.
Thanks, Sam. There are a lot of questions, Case, so I'm not sure we'll get to all of them, but you can check out the chat and maybe you can answer in line. Nico, you had some questions and comments. Maybe do you want to start?
Yeah, sure. Sorry, I'm a bit sick. So did you notice that it clashes with like when you're compiling with an overlay with when you're using some figure environments and that sort of thing, or it's just like smooth sailing?
I have not
Right?
used it.
You just need to add you just need to call a function. I've been coding all day. You just need to call this when you put it in a preamble, this show your work thing, and then you just add it in the figure environment.
Yeah, I have not used the overleaf integration. There's some experimental support. I just put a link into the doc page that talk about overleaf integration into the chat under someone chat. So I don't know whether people can see my chat on my oh, I'm not sharing the screen. But
No,
yeah,
we can't see.
Yeah, I put a chat. So I think it basically does not. I don't think I could be wrong on this. I never use it again, but I think the way that show your work usually work with overleaf is because overleaf support Git, and through that channel it can work through overleaf. But I'm not exactly sure. But there is that doc page, so I encourage you to check it out. Sorry.
No, I meant, sorry, that is a different question. What I meant is if you're using, like, if you have just a simple figure within like a text file, right? But what if you have like a mini page or something more complicated? Will it work in that? So when you wrap it in a mini page, or wrap it in, like, if you have two figures or something?
Oh yeah, I think so. I think so, because show your work does not interfere with like your LaTeX environment. It merely link the script into the repo. So
Right.
I don't think it will clash with any other functionality in LaTeX.
Right. This is brilliant, by the way. Thank you very much for the talk.
Another question is journal, like, does journal like it or something? Is there discussion with journal keeping the script link in final journal PDF? Yeah, good question from Michael. So we trying to provide more permalink like to Zenodo and freeze the version and stuff like that. There is some discussion going on, and it's a good sign to see different journal like AppJ have accepted like 2 of my paper that you show your work, and every time they always talk about like permanent data storage, which I think is very fair point. And I think it's not in the ideal situation that like the journal keeps a copy yet, so it's still using external service like Zenodo, and you rely on the external service. But I think there might be some discussion going on like what to be doing, and I think the more people use it, this will get discussed more, and we can see hopefully a more satisfying solution at some point. Does that
Great.
answer?
And indeed, one of the FJ editors, Frank, is here on the chat and has commented to that thread as well.
Mm-hmm.
All right, let's see. Can it be connected to Overleaf? It looks like, oh, and someone else was asking that as well. So does it work with Overleaf? Is there any problem?
Yeah, I think as I said, there's that talk page that I linked it to in under the reply to that question. I have not used Overleaf myself, but it does have like an integration with Overleaf that will work to a degree. I don't know exactly how well it works, but there's some functionality. I paste the link to the doc page related to Overleaf in that chat for curious people. Please check it out.
All right, great. I'm gonna switch over to Brett. Brett said that he has an answer that is too long to type about how this complements DS9. So maybe Brett can talk to us about Jdaviz versus DS9 or plus DS9.
Sure. So I very firmly believe in the code of conduct of AstroPy, which is that we do not shame each other's tools, and tools have pros and cons. But there are no inherently correct decisions for tools to use for a particular problem. And so I'm not here to say anything about one tool over another tool. Hi, Kelly. I thank you for raising your hand as I mentioned the code of conduct. But I want to say that Jdaviz can do some things that DS9 can do. DS9 can do some things that Jdaviz can do. And your tolerance for Python in particular may determine how much you have to gain by using Jdaviz instead. If you're used to using DS9 from the command line, you might know that there is a command line interface that lets you create regions and open complex data sets in particular views. And there are all kinds of ways that you can do that from the command line. But the command line interface for DS9 may be challenging to use. And if you already know Python, the Python interface, especially through a Jupyter notebook, may be much more intuitive for doing that kind of process where you interactively load and inspect and visualize and then analyze the data. And so the line analysis tools with error propagation and units, for example, is something that you get in Jdaviz, which you don't quite get in DS9. And of course, all of this is done in a Jupyter notebook so that you can take the parts out and do more complicated workflows if you want at any time. So if you do that preliminary Gaussian fit, you get a centroid to the line center of an emission line. And then you're saying, okay, well, now I want to do MCMC inference to get a posterior for the centroid. It would be difficult to do that in DS9, but you'd already be in a Jupyter notebook potentially for JDAVIS. So those are some things to take into consideration when deciding what to do. Would Kelly like to jump in here?
Yeah, let's thanks for that thoughtful answer though.
No, I just raised my hand because I have a different question. So if we're ready for a new question.
Please,
Brett,
go ahead.
great. So I'm curious. I mean, Brett, as you know, I just like to ask the question over and over again. I'm very interested in using JDAVIZ and the spectral analysis capabilities embedded in my own website. And I'm curious about the future potential for that, or the idea of maybe being able to launch it. Like I click a button from an external website and then somehow it launches a JDAVIZ something somewhere with a spectrum where I give it a link. Yeah, thoughts on that?
Of course. So there are two primary ways of doing that right now. And both are demonstrated by the example that I showed you from MAST. So MAST hosts all of the data from Space Telescope, and MAST provides a website that has an instance of JDAVIZ running within it. And you can use that instance of JDAVIZ to explore your data. It is possible for you to do the same thing on your server. So if you have a server and you have access to your data and you can make a website public, you can make an instance of JDAVIZ that displays your own data in the same way that MAST does. That's a little bit complicated because it requires you to understand the web development part of it, which is often the thing that people are least comfortable with, but it depends on your tolerance for that. Another thing that you can do, which MAST also does, is it provides a download link for a Jupyter notebook. The download link will give you a notebook where the URL for the data that you want to display is just pre-populated in the notebook. So that suppose you had a spectrum that you wanted someone to be able to visualize locally, you could have a link in your database that says, when I click this button, pre-populate a notebook with the URL to the spectrum that I intend to download and display on JDAVIZ on my machine. And then you would give the user the text file, which is a Jupyter notebook. And when they run it on their machine, they'd be able to do the download from your database and then visualize and interact with the data locally. MAST currently does both of those things, and we know that both can be supported, but we're spoiled at Space Telescope because we have full-time staff who work on MAST who make that happen. So if you have a web admin, or in your case, Kelly, you have someone named David who might be able to help, that is a workflow that might work for you.
But yeah, that idea of downloading the notebook and then running it locally is actually a really good one. That one might be easier to implement than the other one. Thank you.
Absolutely. That's definitely the most straightforward way to do it.
Great. Both of you are doing a fantastic job of answering all the questions in the chat. It's making my job hard at finding things that aren't answered. Wow. And I was just going to ask something, and Case just answered it. Cool. Case, I'm going to ask then my other question, and that is, and you kind of mentioned this with simulations. Zenoda has a 50 gigabyte limit. And simulation files output single files can be terabytes in size. And so it's not clear to me yet how to do reproducibility and give people access to the raw outputs, because there's really no place to host those. So you have to give them distilled products. This
is a great question because I do like quite large scale stuff, and it's important. I think this can be solved ultimately if everything has publicly tracked, everything's open source and everything is version control. So like one of my friend from our office mate, Matteo Renzo, who is new faculty in Arizona, he run a lot of mesa simulation, which the output could be large. So instead of storing the output, he gives the exact configuration version of the code onto Zenoda, which people can fetch and run it and produce the artifact, and that can later be used in generating figures.
So we do that as well, but our simulations can take a year to run on 10,000 GPUs.
Right.
And those machines can go away. And that operating system or those compiler versions can go away. You know, CUDA's proprietary. You may not be able to get that version anymore. So at some point, you may not be able to reproduce the exact environment things were run on.
Yeah,
So
I agree. You know, at some point there will be a computational limit, right? You know, if ultimately the paper takes like 100 million CPU hours and you want to reproduce it, then you need to have 100 million CPU hours. And I think that's pretty much still in debate, in discussion, what we can do to alleviate a problem. But I think, you know, to reduce the data, to keep it some part that goes into the draft, we can have some measure to do that, but it's not, we don't have like a final answer to that question yet.
yeah, that's something I struggle with because there's no way to store the data at some point. One last question, if someone wants to raise their hand. And both of you, thank you again for being so active in the chat and answering all the questions. It was fantastic. All right, I don't see anyone raising their hand.
What's next
So,
month?
what is next month? I have to find the webpage. We're actually looking for one more speaker for next month. Hint, hint.
We have Top Cat and Stilts.
Oh yeah, Top Hat and Stilts. Thank you.
You're welcome.
Top Cat and Stilts, and we're looking for one more speaker. And then just a reminder as well. Let us know if you want to talk. Raise an issue on GitHub. If you can reach out to us as well. We especially appreciate talks from junior developers, and this is sort of a low pressure environment for you to get some exposure for both yourself and your project. So please do reach out. I'll leave it at that.
Yeah, just want to thank again, Brett and Kaze,